Right, here's a walkthrough for Edexcel Paper 2023. It's Physics, Combined Science, and it's Paper 2, the higher tier. You get 1 hour and 10 minutes, and it's worth 60 marks. Question 1, Part A. Figure 1 shows some of the apparatus that students use to determine the resistance of a piece of iron wire. Add connecting wires, a voltmeter and an ammeter to complete the circuit in Figure 1 so that the students can determine the resistance of the piece of iron wire. Right, well, connecting wires will go something like that. We need to put an ammeter in, so that's a circle with an A, and that goes in series with the iron wire. And you need to put a voltmeter in, so that's a circle with a V, and that needs to go in parallel with the iron wire. Part B. The students extend the investigation to determine how the resistance of the wire changes with its length. Give the name of one additional piece of apparatus the students would use or would need. That's a ruler to measure the length. Part 2. Figure 2 shows a graph of the results. Draw a straight line of best fit on Figure 2. Right. Does it need to go through the origin 0, 0? Well, if the length of the wire was nothing, the resistance would be nothing. So yes, we do need to go through 0, 0. What I like to do is just draw it from 0, 0 up to the end point and just see if that looks reasonable. Does it go through quite a number of the points? Yes, it does. Does any points it doesn't go through seem to be the same number above and below, there or thereabouts? Yes, it does. 2 below, 1 above. That's about as good as we're going to get. I'm happy with that. Part 3. Use Figure 2 to estimate the resistance of a 100 centimetre length of the iron wire. So there's 100 centimetres. We need to continue that line. So if I draw it like this, does that seem about right? Yes, it does. And then if you go from 100 centimetres up to there and then come across from the line, that is 3 ohms. 3.00 ohms. Part 4. The variable resistor shown in Figure 1 is used to prevent the iron wire from becoming too hot. Explain how the variable resistor is used to prevent the iron wire from becoming too hot. So a variable resistor increases the resistance of the circuit. This keeps the current smaller. This prevents the iron wire from becoming too hot because current heats up the wire. So because we've kept the current smaller, that stops the wire from getting hot, like they said. Question C. The potential difference or voltage across another piece of wire is 1.56 volts, so that's V for volts. The current in the wire is 0.45 amps. Current is I. Calculate the resistance, so R is our target of this piece of wire. Use the equation V equals I times by R. Right, we need to rearrange that using the magic triangle. So I times by R goes on the bottom and V must go on the top shelf. Cover up what you're looking for, so we're looking for resistance, and that leaves V divided by I. So R equals V divided by I. Let's pop the numbers in. V was 1.56 volts and I, the current, was 0.45 amps, and that comes out as 3.46 recurring ohms. And we can round that up to 3.47. I've done it to 2 decimal places because both of their numbers were 2 decimal places. Question 2, Part A. Which of these means change in state from solid directly to gas? So to go from a solid directly into a gas, that's called sublimate. I've wrote all the other things on there as well, just in case. Solid to a liquid is melting. Liquid to a gas is boiling or evaporate. Gas cooling down to a liquid is condense. Liquid cooling down to a solid is freezing. So going from the solid to the gas is called sublimating. Going from a gas right down to a solid is called deposition. But that's more of a chemistry thing. We don't really talk about it in physics. Part B. An object has a mass of 7.22 times 10 to the minus 2 kilograms. So that's our mass. And a volume of 2.69 times 10 to the minus 5 meters cubed. So that's V for volume. Calculate the density rho of the object. So that is our target. And use the equation. Okay, we can just pop the numbers straight in because we don't need to rearrange it. And that comes out as 2684.0. And we've divided kilograms by meters cubed. So 2,684, and the unit is kilograms per metre cubed, because we've divided kilograms by metres cubed. Part C. Aluminium has a melting point of 660 degrees C. The absolute zero of temperature is minus 273 degrees C. Calculate the melting point of aluminium in Kelvin. Right, to get the temperature in Kelvin, you take the temperature in degrees C's and you add 273. So that equals 660 degrees C plus 273, and that comes out as 933 Kelvin. If you wanted to go and work out what the temperature in degrees C was, and they gave you the temperature in Kelvin, you take away 273. Part 2. Describe the motion of particles in liquid aluminium. So really just describe the particles in any liquid, and it's the motion, not the structure. So the particles move randomly, they move freely, they bump into each other, they have various speeds. That means they've got various kinetic energies as well. And they move faster than the particles in a solid. All they can do in a solid, remember, is vibrate. So any of them for 2 marks. You pick which ones you like the best. Part D. A student determines the volume of a piece of metal by measuring the volume of water that it displaces. The student wrote the following in his notebook. I put some water into a measuring cylinder. I put the piece of metal into the water in the measuring cylinder. I took the reading of the new water level in the measuring cylinder. This was the volume of the piece of metal. Right, well I can see some mistakes there. The student's description is incomplete. Suggest 2 sentences that the student could have included to provide a more complete description of the correct procedure. Right, I put some water into a measuring cylinder. they should have said, I took a reading of the volume. I put the piece of metal into the water in the measuring cylinder. Right, they should have said that they fully submerged the metal. Metal was fully submerged. I took the reading of the new water level in the measuring cylinder. Right, that's good. This was the volume of the piece of metal. Nah, it wasn't. You need to subtract the original reading of the volume from the new water level. Subtract the new volume from the original volume. Right, so there's 3 different readings there. You decide what you'd want to put in there. Take reading of the volume of the water without the metal. Make sure metal is fully submerged. Right, I've just realised that's the wrong way around. It should say subtract original volume from new volume. So the new volume might be 100 mils. The original volume might have been 80 mils. So 100 take away 80 means that the metal's volume would have been 20 mils, which is 20 centimetres cubed. Not that we're really bothered. I'm just doing it as an example to show you. Question 3. Part A. Figure 3 shows 2 magnets with their north poles facing each other. On figure 3, draw the shape and direction of the magnetic field between the 2 magnets. Right, well remember, the magnetic field comes out of the north and goes into the south. Now the thing is it's going to come out of that north and it's not going to go into that north. It's going to get repelled by that north. So it'll come out like that and then it'll get pushed away. And it would actually go all the way back into its own south. So it'll come out this way here. This one will come out there. This one will come out there. And they'll be repelled away from each other like that. Now, just in case in your exam, it said you've got a north and a south, draw the magnetic field. It would come out the north and go straight into the south this time. And that would be a little bit circular like that, and that would be a little bit circular like that. Part B. Figure 4 shows a toy that has a plastic cylinder, a plastic base and 2 similar magnets. Each of the 2 magnets is in the shape of a ring. The upper magnet seems to float in the air above the lower magnet. Describe the forces acting on the upper magnet. Use the idea of magnetic fields in your answer. Right, well the forces acting on the upper magnet, you'll have weight acting downwards on the upper magnet, and you'll have a repulsion acting upwards. And if it's floating, the weight must equal the repulsion. Equal force but opposite in direction. And why do you get the repulsion? Well, it's magnetic fields interacting. So that's how you get the idea of magnetic fields into your answer. Magnetic fields from the 2 magnets interact. This causes a repulsion force upwards on the upper magnet, and the upper magnet has a weight force downwards, and weight force down equals repulsion force up. So we'll definitely get our 3 marks there. You decide which 3 things you want to see. Question C. Figure 5 shows a current carrying wire between the poles of a magnet. Part 1. The magnet and the wire each experience a force when there is a current in the wire. Number 1. State the direction of the force on the wire, and number 2. State the direction of the force on the magnet. Right, well, we need to use Fleming's left-hand rule, or left-hand motor rule. You've got your thumb pointing up. You've got your first finger pointing to the right. That shows you the magnetic field. Your thumb showed you the movement. And the second finger shows you the current. So the first finger goes from the north to the south. Knuckles is north, fingertips is south, so you'd have to point your first finger that way. The current is coming this way, it's all at 90 degrees, so you can see the current's coming out that way. So that means that the movement or the force would be upwards. So state the direction of the force. It's the force that creates the movement, so that's going upwards. Now, if the force on the wire is going up, that must mean that the force on the magnet is equal in size but opposite in direction. So that's going downwards. Opposite in direction. Part 2. The force on the wire is 0.15 newtons, so that's F. The current on the wire is 2.7 amps, that's I. The magnet produces a field with a magnetic flux density of 0.5 teslas, that's B. Calculate the length, so L is our target, the length of the wire in the magnetic field. Use an equation selected from the list of equations given at the end of the question paper. So we're looking for an equation that's got F, B, I and L. Here we go. F equals B times by I times by L, or F equals Bill. Make sure you know these equations. So F equals B times by I times by L, and we need to calculate L, so we'll need to whip up a magic triangle with 2 multiplied signs on the bottom because we've got to multiply 3 things. So that's B times by I times by L goes in the bottom, so F must go on the top. We're looking for L, cover up L, and we are left with F divided by B times by I. So L equals F divided by B times by I. Pop the numbers in. So the force was 0.15 newtons. The magnetic flux density was 0.5 Tesla. And the current was 2.7 amps. And if you pop that into your calculator, that comes out as 0.11 recurring. And that'll be in meters. So the answer is 0.11. I've left it to 2 decimal places because that is to 2 decimal places, that's to 2 decimal places. I know that's only to 1 decimal place, but always do it to the greatest number of decimal places that they've done it to. Question 4. Part A. Figure 6 shows part of the inside of a pen. The pen contains a spring that can be compressed. The spring constant of the spring is 260 newtons per metre, so that's K. Calculate the force, so force is question mark, needed to compress the spring by the amount shown in figure 6. So extension equals 6.2 millimeters. Now you'll need to convert that into meters because this is in meters. So 6.2 times 10 to the minus 3 meters. Putting times 10 to the minus 3 on the end is the same as dividing it by 1,000. And the reason you want to divide it by 1,000 is because there's 1,000 millimeters in a meter. Give your answer to an appropriate number of significant figures. Well, this number is to 2 significant figures, and this number is to 2 significant figures, so we'll do it to 2 significant figures as well. Now, they haven't given you the equation, and they don't tell you to look it up at the back. So this is an equation that you need to memorise, and it's F equals K times by X. So we don't need to rearrange it, we just need to pop the numbers in. So K was 260 newtons per metre, and the extension is 6.2 times 10 to the minus 3 metres. Pop that in your calculator, and that comes out as 1.612. And that's newtons. And if we're going to do it to 2 significant figures, that just comes out as 1.6. Part 2. A student removes the spring from the pen and investigates the compression of the spring. Figure 7 shows the equipment and the procedure that the student uses. The student presses down on the spring to change its length. The electronic balance measures the force applied to the spring. Describe how the student can determine the change in length of the spring. You may add to figure 7 to help your answer. Right, well, we just need to see how big is the spring when there's a force of nothing on it, and then what is the new length of the spring when the force is on it. And we'll be able to get the change in length by doing the original length, take away the new length. So, measure the length of the spring with 0 newtons on it. We'll call that the original length. Then measure the length when the force is applied. We'll call that the new length. And to get the change in the length, just do the original length, take away the new length. The other way you could have done it is F equals K times by X once again. So therefore, X would be F over K. Tells you that the force was 0.39 newtons, and it's the same spring as before, so the K value was 260 newtons per metre. And you could pop that in your calculator, and that would come out as 1.5 times 10 to the minus 3 metres, which is 1.5 millimetres. And that sounds about right. So either of those ways is acceptable. Part 3. The student finds it difficult to make an accurate measurement of the change in length of the spring using the equipment as shown. Describe one way that the student could improve the procedure, and that's worth 2 marks. Right, let's go back up and have a little look. Right, that spring is quite far away from the ruler. So you could either move the spring in closer to the ruler, or you could put a pointer on the top of the spring, and that'll make it easier to see what the measurement is. Move the spring closer to the ruler. This will reduce parallax error. Or put a pointer on the top of the spring. This will make it clear what the length is, because it will also reduce parallax error. Parallax error is when your eye is not level with what you're trying to look at. So as your eye goes up and down here, it'll make the spring look like it's at a different length. Moving the spring closer, it'll stop that happening, or if you've got a pointer, that'll stop the parallax error from happening as well. Part B. Figure 8 shows a different spring hanging from a hook fixed to the ceiling. A block hangs from the other end of the spring. The weight of the spring is 1 Newton. The weight of the block is 5 newtons. The force exerted on the top of the spring by the hook is... Right, you've either got 4 newtons down, 4 newtons up, 6 newtons down or 6 newtons up. So the force by the hook will have to be equal in size but opposite in direction compared to the combined weight of the block and the spring. So that'll be 5 newtons plus 1 newtons equals 6 newtons down. So therefore this needs to be 6 newtons up. So the answer is D. Question C. Figure 9 shows 2 forces, P and Q, acting at point X. So X is the object, you've got P, which is acting downwards with 30 newtons, and Q is acting horizontally across with 40 newtons. And the diagram is drawn to scale. Complete the diagram in figure 9 to show the size and direction of the resultant force R on point X. So this is tip-to-tail addition of vectors. So a vector has size and direction. So P is a vector and Q is a vector. So if we were to pick P up and add it to the end of Q, that's what it would look like. And if we were to take Q and add it to the tip of P, that's what it would look like. And so our resultant goes from the start where X is down to the end where that is, where these two vectors meet. So it's a parallelogram of forces. Now the problem is with this being on a computer screen, when I measure these lengths here, they're going to be different to what you measure if you've got a print out of this paper. Now on my computer screen, this length of P is exactly 8 centimetres. So what you need to do in your exam is you say 30 newtons divided by 8 centimetres equals 3.75 newtons per centimetre. And you could also double check it by measuring the length of Q. Now when I measure Q on my computer screen, it's coming out as 10.6, sort of 10.7 centimetres. So in your exam, you'd measure your length and then you'd go 40 newtons divided by the length that you've measured. And then that'll come out as, now it's 3.77 newtons per centimetre. Now as I say, that value is between 10.6 and 10.7. So I'm going to take this number as being the correct number. This number up here should have came out as 3.75 as well. So that number there was actually 10.66 and then that comes out as 3.75. Like I say, on your exam paper it'll work out perfectly. So now what you do is you need to measure the length of this resultant red arrow. Now on my screen it comes out as 13.5 centimetres. and we know that each centimetre is 3.75 newtons. So if I do 13.5 centimetres times by 3.75 newtons per centimetre, that comes out as 50.625 newtons. Now when I've checked the mark scheme, what I've done there is correct, and the range that they'll accept is between 48 to 52 newtons. Question 5, Part A. An electric car is travelling at a speed of 16 metres per second. So that's our velocity, V. The total mass of the car is 1,200 kilograms, so that's our mass M. Calculate the kinetic energy, so kinetic energy is our target, in kilojoules of the car. Right, so kinetic energy equals a half times by the mass times by the velocity squared. So that comes out as a half times by 1,200 kilograms times by 16 squared. And that equals 153,600 joules. Now they want it in kilojoules, so you'd have to divide that by 1,000. So that equals 153.6 kilojoules. Remember to square the 16 first, then you can multiply it by the 1,200 and then multiply it by 0.5, which is obviously the half. Part 2. On a journey, the car transfers energy from the battery at an average rate of 17.5 kilowatts. So that is power P. The battery in the car transfers a total of 126 megajoules of energy, so that's E, before it becomes discharged. Calculate the time taken, so time is our target, for the battery to become discharged on this journey. Give your answer in hours. Right, so the first thing is we're going to need to convert kilowatts into watts. So there's 1,000 watts equals 1 kilowatt. So that's going to be 17.5 times 10 to the 3 watts. And this is megajoules. So 1,000,000 joules equals 1 megajoule. So this number is going to be 126 times 10 to the 6 joules. Now the equation you need is power equals energy transferred over time. We need to rearrange that. So magic triangle. E's on the top shelf out here, so it goes on the top shelf in here. And then just put P and T down the bottom. We're looking for time, so cover up time, and we're left with E divided by P. So therefore time equals energy divided by power. If we pop the numbers in. So that'll catch a lot of students out if you forgot to put the correct powers in. That's usually what happens if a student makes a mistake. And that comes out as 7,200. And that'll be seconds. Now we're going to need to divide that by 60 seconds per minute, and then also divide it by 60 minutes per hour, and that comes out as exactly 2 hours. Part 3. Figure 10 shows an electrical device connected to the wheels of an electric car. The electrical device is used as a motor when the car accelerates and as a dynamo when the car decelerates. Explain how using the device can help to increase the time that the car can be driven before the battery becomes discharged. Right, the dynamo is a device that when you turn it, kinetic energy can be converted into electricity. And that electrical energy can be used to recharge the battery so the battery lasts longer. So basically every time the car decelerates, the dynamo kicks in and the kinetic energy from the wheels would get turned into electrical energy. Clever stuff. Part B. The battery can be recharged at a charging point. The charging point provides an average current of 15 amps, so that's I current, to the battery at a potential difference voltage of 400 volts, so that's our voltage value. It is claimed that 126 megajoules of energy, so that's E, can be transferred to the battery in less than 6 hours, so that's our time. Comment on this claim. Use this equation to support your answer. Right, so if we pop these numbers into this equation, that time should come out less than 6 hours if the claim is correct. So let's pop the numbers in. 126 megajoules, remember, a megajoule is times 10 to the 6 joules. And we divide that by the current, which was 15 amps, and multiply that by the voltage, which was 400 volts. And that comes out as 21,000 seconds. Right, we need to turn that into hours. So 21,000 seconds, again, divide that by 60, because there's 60 seconds in a minute, and we also need to divide it by another 60, because there's 60 minutes in an hour. And that'll come out as 5.83 recurring hours. So they've claimed that 126 megajoules of energy can be transferred to the battery in less than 6 hours. That's correct. It takes 5.83 hours. So they are right. The claim is correct. It only takes 5.83 hours to transfer 126 megajoules of energy. Part 2. Calculate the total charge that moves into the battery while it is being recharged. Use the equation E equals Q times by V. So we're looking for Q. So we're going to need to rearrange this equation. So if we pop it into a magic triangle, Q times by V goes on the bottom and E must go on the top. Cover up what you're looking for, which is Q, and we get left with E divided by V. So Q, the charge, equals the amount of energy divided by the voltage. So the amount of energy was 126 megajoules, which is 126 times 10 to the 6 joules. And we'll divide that by the voltage, which was 400. And that comes out as 315,000 coulombs. Question 6, Part A. Figure 11 shows a pulley system that enables a person to lift a heavy barrel. The person pulls down on the rope to make the barrel rise through 1.2 metres. The work done against gravity on the barrel is 1,800 joules. Calculate the weight of the barrel. Use the equation work done equals force times by distance moved in the direction of the force. Right, so the work done was 1,800 joules. The distance moved in the direction of the force was 1.2 metres. And we are looking for the weight, which is basically the force. So we need to rearrange that equation. So if we did a magic triangle, we'd have the force times by the distance, and that equals the work done. So the force is basically the weight, so that's what we're trying to find out. So cover up the force, and we're left with work done divided by distance. So that equals 1,800 joules divided by 1.2 metres, and that equals 1,500 newtons. Part 2. The efficiency of the system is 64%. Calculate the total work done by the person. Use the equation efficiency equals work done against gravity on the barrel divided by the total work done by the person times by 100%. Now we're going to have to rearrange this equation. So what I like to do is I like to get rid of that 100% by converting that percentage into a decimal. And you do that by doing 64% divided by 100%. That'll just equal 0.64. Now we're going to need to do a magic triangle. So we've got work done against gravity goes on the top. So work done on the barrel. And we're going to get the efficiency times by the total work done on the bottom, and we're trying to work out the total work done, so I'll cover that up, and what you're left with is the work done on the barrel divided by efficiency. So the work done on the barrel, if we go back to the original question, was 1,800 joules, and we need to divide that by the efficiency, which was your 0.64, and that comes out as 2,812.5. So basically that person had to use 2,812.5 joules to lift that barrel 1.2 metres. Now by lifting it 1.2 metres, it's gained 1,800 joules of energy. So he's put 2,812 in, and he's only got that out. And that's because the system is only 64% efficient. So I hope that makes sense, because otherwise it's quite a tricky question, to be honest. Part 3. Some energy is wasted due to friction. Suggest another reason why some energy is wasted in using this pulley system. Right, so they're basically saying that some is wasted due to friction. So you're not allowed to say heat and sound. You've got to come up with another reason why some energy is wasted, except for saying heat and sound. Right, let's have a little look at the picture again. Right, do you see this big heavy thing? that is also going up. You see in this picture how it's already gone up. So we've worked out the weight of the barrel to be 1,500, but we are actually lifting this pulley and the ropes at the same time. So some energy will have been wasted in lifting the pulley and the ropes. And also, rope is a little bit stretchy, so the rope stretches. That'll be another reason why some energy gets wasted. So the rope and the pulley also has mass, which needs to be lifted, and the rope will stretch, which will cause some of his energy to be wasted. So the key thing there was to look up on the word another. I mean, they've put it in bold so you can't miss it. But yeah, if you just put heat and sound there, you wouldn't get the mark for it. Part B. The last question, our 6 marker. A student has the equipment shown in figure 12. Devise an experiment to investigate how the efficiency of the pulley system varies with the weight of metal being lifted. So efficiency of pulley with the weight of metal being lifted. Your answer should include how you will use your measurements. Right, so they've gave us a spring balance, cubes of metal and a meter ruler. Right, if we're going to get the weight of metal being lifted, we could use the spring balance. Use the spring balance to measure the weight of a cube of metal. Right, now if we hang the cube of metal on to this hook, and then what we can do is if we put the spring balance on this end, we can pull this end, and we know the weight of that. So just say the weight of that was 100 newtons. I wonder if the pulling force will be 100 newtons. Well, it won't be, because that's the whole point of using a pulley system. It makes it easier to lift. So let's say that that is only 80 newtons. Hang the cube of metal on the hook. Pull the other end using the spring balance. Measure the force needed to pull. Use a ruler to see how high the weight is lifted. Also, use the ruler to see how far the spring balance on this end moves. Now, if we get that distance and we get that weight, work done will equal, that weight is a force, remember, so it'll equal that force times by that distance. So calculate the work done on the weight by force times by distance, and if we also get that distance there times by this force here, we'll get the work done by the person. So that force there was the weight of the cube. Then we can calculate the efficiency by calculating the work done on the cube divided by the work done by the person. Then we can change the weight and repeat everything we've just done. Repeat the above steps to calculate the new efficiency and compare efficiencies. I'm not going to kid you, that's quite a tricky question, that one. Now that would get you 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 different things I've put there just to get 6 marks. Now, obviously you wouldn't have to put them all to get 6 marks, but which ones of those would you leave out? I'll be honest, I'm not sure. As I say, that's a very tricky question because you can't really get 6 marks just by saying 6 things. There's quite a number of steps there you've got to put to give the full answer. Your answer definitely should include how you're going to use your measurements. So I would do a combination of a few of these steps and make sure that you put the calculations in, because that's basically telling you what you're going to do with your measurements. Let's just hope another big question like that doesn't come up. Right, I hope that's helped you. Anyway, if you've been bashing your way through these videos right till the end, well done. It will definitely pay off for you. That is an OB guarantee. Right, work hard, be nice, and I'll see you in the next video. Bye for now. Want to see more videos like this? Subscribe to my channel, GCSE Physics Explained.